So last time, in the previous packet, we learned about interatomic force, energy. We did a quiz. Now we want to see how the atoms are arranged inside the material. What we are going towards is to understand steel. So that's why we kind of emphasize the microstructure of metallic materials, because you will see that soon we are going to then just talk about different kinds of materials. So we go from the very sciencey part of this class towards the more engineering parts. So in terms of reading, textbook has a small section, 2.2. The other book, which is on the syllabus, has chapter 3 for more readings. So we want to start with how the structure of the lattice looks like, and what are the things that can go wrong inside the structure, and what implications we will see in engineering properties. So let's get started. You may remember this slide from before. Does anyone remember what these ships were and what happened to them?
They were Liberty ships and then they went
Exactly. Do you remember why they broke?
they went past the transition sensor.
Exactly. Because they were okay at room temperature, but when the temperature was below a certain temperature, then their behavior changed from ductile to brittle. And that's why they developed those cracks and they broke. Now, something that you may when I was teaching this before, I told you this depends on the microstructure. Not all the metals are going to have this kind of behavior. And you saw some strange things written here, BCC, FCC. Today is the day to learn what these things are. So microstructure matters. You can see that, for example, if the metal has a FCC microstructure, it doesn't have this problem. But BCC has this problem. So we want to find out what these mysterious BCC and FCC, what they stand for, what these are, and to learn a few things about the microstructure of metal. Last time, you saw this curve. You saw the energy versus the interatomic separation or spacing. This is what we looked at last time. It turns out that where the material actually stands on this curve depends on the packing. So if the material is just randomly packed, it's not very dense, the atoms are not very closely packed, you are not at the most stable place, you are not at the minimum. A material, when it is very densely and closely packed, the energy will be minimum. It will be very stable. So ordered and packed atomic structure tend to have lower energy. They're more stable. Now we want to learn more about this packing, what these atomic structures are. It turns out that materials may be very well ordered, like you see up there, nicely packed, densely packed together, or they may be very randomly oriented, almost like a liquid, but they have some bonds in between them. And in the first case, we call them crystalline microstructure, so crystals. Second case is amorphous. And it turns out that one of the materials which matter to us a lot as civil engineers, the steel, has crystalline structure. And there are other materials, like for example, asphalt has amorphous structure, polymers, glass. just to give you some more information, this crystalline structure can play a big role in how the material would behave. So even if you have the same kind of atoms here, silicon and oxygen, depending on the macrostructure, it can be quartz or it can be glass. It can be different materials. Macrostructure matters. And if you want to kind of visualize how a crystalline solid is different from an amorphous solid, for example, you can think about a crystalline solid as a nice airport parking lot where all the cars are nicely parked. And this is actually a real picture of a salt crystal, and you see that everything is really nicely oriented. This is a real picture using atomic force microscope. So it looks just like a parking lot. And if you want to compare it to a non-crystalline solid, it would be like that, going from a nicely packed parking lot to something a little bit more chaotic. And again, why do we care about all of that? That's the bold statement that you see up there. It matters to us because eventually it has a lot of effect on the macroscopic engineering properties that we are interested in. So you have the same atoms. If they are nicely oriented, you are going to get quartz. If they're a little bit chaotic, you are going to get glass. They are two different materials. Now, we want to learn about the macrostructure of a steel because this material matters to us. You saw that in the case of Liberty ships, this not understanding of what is going on led to disaster. So we want to understand what the macrostructure of a steel looks like. So just some introduction. Metals in general tend to be densely packed. They have crystalline structure. There are different reasons why, because metallic bonds, if you remember from last time, is non-directional. Remember an ocean of electrons, and then you have the protons and neutrons in them. It's non-directional. It's easy for the atoms to pack nicely. So they have crystalline structures. Now let's learn more about their structure. The first thing we need to learn about the crystalline structure is this concept of unit cell. So I want you to look at this structure here. The unit cell is the smallest unit that you can take out of the structure, and it is, if you put this unit together many, many times, you're going to construct this structure. So it's called unit cell. It's the building block of the macrostructure. But we typically just study this unit cell because then you don't need to study the whole thing. If you know everything here, then the whole thing would be just a multiplication of what you see in the unit cell. And the simplest kind of unit cell is called simple cube structure, SC. This is not a metal, but I start with that because this is very simple. What do we have? We have, so the unit cell is just a cube, and then you have these atoms here. There are two different ways to represent a unit cell. Pay attention to the difference between them. So in one, you just see the location, but in the other one, you actually see how the atoms are located with respect to each other. For example, you see that they're actually touching, like at each point. Now, there are a few definitions you need to learn here. One is the coordination number. So if you pick any atoms inside this microstructure, how many atoms this is connected to? Here, I've kind of isolated this here, so you kind of see that each atom is connected to 6 other atoms. So the coordination number is 6. Now, this is not as important as the next thing that I want to ask you. If someone asks you how many full atoms are inside this unit cell, what do you answer? To answer that question, you always have to look at this kind of schematic. That's more helpful. So the question is, this is the unit cell of simple cubic structure. How many whole full atoms are inside? I give you 30 seconds to think. Either one, they're the same. Inside this cube, how many full atoms are there? Just one. Everyone sees that? This is one. Everyone sees that there is only one. Think about an apple, you cut it, right? And then you put it on the corners. It's just one apple. If it's very round. Convinced everyone this is one? The next important thing is the relationship between the radius of the atom and the size of the cube. If you figure these two things out, then you know everything about the microstructure that I want you to know for this class. Here is kind of easy, right? What's the relationship? Again, 30 seconds. It's easy. Yes. Remember, this is the simplest one. So we start with something that we all can agree on, and it's not a metal yet. But I have good feelings that we are going to be okay. So here, when I'm asking how many atoms per unit cell, I guess this whole class can confidently say 1. And the relationship between R and A, so R is A over 2. Now this brings us to an important definition, which has a lot to do with the density of materials. And this is this atomic packing factor. It turns out that materials have different densities because they have different atomic structures, atomic packing. And that defines their density. And it's very easy to calculate. So all we have to calculate is to look at the unit cell and see how much of the unit cell is filled with atoms. So you want to see what is the percentage of the unit cell which is filled with atoms. So volume of atoms in unit cell over the volume of unit cell. How do we calculate that? Well, we all agreed that there is one full atom in this unit cell, right? What is the volume of one sphere with radius r? That's the harder question. Exactly. 4/3 pi r cubed. Perfect. And then we have to divide this by the volume of unit cell, which is easy. Each side is A, so it's just A cubed. And that's when we need to have the relationship between A and R to be able to cancel it. So you all smiled when I said, oh, what is the relationship? It was so obvious. So that you can just substitute for A equal to 2R, or vice versa. You can substitute for R in terms of A. And then just calculate this. I think I have a nicer, yeah. So if you do the calculations, I don't know how many of you did, you should get 0.52, if I haven't made a mistake. Right? So the atomic packing factor for a simple cube structure, which is kind of not very interesting to us, but it's simple, so we wanted to start with it, is 0.52. This means that 52% of the volume of unit cell is filled with atoms. That's what it means. So the fancy name has a very simple explanation. Now we want to see about metals, because this is what we are interested in. We are engineers. We don't care about polonium. We want to see what is going on with the metals. It turns out that the metals that we care for have typically two types of macrostructure, and some others have this, the third one. A is called body-centered cube structure. So what you saw, the B, no, I'm sorry, this is face-center cube. So the mystery that I showed you in the beginning for the Liberty ship, FCC, it means that if you had a way to look at the macrostructure, it would look like that. And the one which had problems, and it has this transition temperature, is this body-centered cube. And this one is hexagonal. And we are going to learn about this. And the names kind of make sense, right? Look at these figures a little bit. You see both illustrations side by side. It's important that you understand that even if it looks like that, it is actually like this, meaning that these atoms are actually touching in the middle. They are not far apart as you can see here. It's densely packed as you can view here and here. There are nicer pictures later for that one. So we want to start now to learn about these microstructures. And I think we start with BCC. So it's called body-centered because you see there is an atom in the middle. The other ones, you have atoms on each face. So that's why it's called face-centered. So, a nicer picture. We start with body-centered cube structure, BCC. And iron, some types of iron have this kind of microstructure, as you can see. The coordination number here is pretty simple. There are 8 atoms around each atom. You can see that? Just pick the middle one, the easiest. Right. Now, the question is, how many atoms do we have in this unit cell? We have 2. Everyone sees that? So this is like simple cube, and then in the middle you inserted another one. So it's 2. So in FE exam, there are some questions. I have some FE exam questions at the middle of this packet, or at the end of the packet that you have in your hand. So the question is just, counting the number of atoms in a unit cell. So it's pretty simple. And here, so 1 at the center, 8 corners. Each one of them are 1/8 So that gives us 2. So you can see what we are going towards. We want to calculate the atomic packing factor. So we are convinced that the unit cell comprised of 2 whole atoms, and the coordination number was how much? How many? 8. It's kind of easy to see here. Now, to find APF, we also need to know the relationship between A and R. This one needs a little bit of attention. We cannot really say A is equal to R because they're not really touching. What we know is touching is along the diagonal. Right? We know that along the diagonal, these 3 are touching. I think I have a better picture. Yeah, I like this better. So these are touching. So we have here A, here we have A. We can calculate this in terms of A is just the square root of 2 times A. And then here is A. And since those are touching along the diagonal, then we know that that is 1R plus 2 half R's, which is 2R. R, 2R, sorry, it's 4R. So this is 4R, and at the same time, it is square root of 3 times A. So here we have A, here we have A. So I write everything in this slide, because I like the, so this one will be the square root of 2A. I don't need to explain why, right? You know. Okay. And then this is A, and kind of this triangle comes here. So here is square root of 2A, A. Then you have a square root of 3A. At the same time, this is equal to 4R, because those atoms are touching. So the relationship between A and R is then established. Now, take 1 minute. You can talk to each other, etc. Calculate APF. We know how many whole atoms. We know the relationship between A and R. We have everything to calculate. We can talk to each other. No problem. Look back. Oh God. As usual, I should see 3 correct answers before. Correct answers here. There should be a number, just a number. One correct answer. One correct answer so far. Two correct answers. So remember that atomic packing factor is nothing else but what is the percentage of volume which is full with atoms. So how much atom we have over the entire volume. We have, you all were agreeing with me that we have two full atoms. Each one has this volume, and this is the volume of unit cell. We use the relationship between A and R. You can do either way. Either you write A in terms of R or vice versa. And then A will cancel out. And you should get 0.68. Now, if you compare a material, let's say if you had the same atom, if the macrostructure was a simple cube versus a body-centered cube, which one would you think would be heavier, would have a higher density? Simple cube or body-centered cube? Body-centered cube, because APF is higher. Yes, everyone listen to what I just said? So APF has a close relationship, as you will see very soon, with density. Because it tells you how much matter there is inside the material. Now, the second structure is the face-centered cube. And that's FCC for short. Again, we are looking at the unit cell. Here, aluminum is an example, which is probably interesting to us. Now look at this one and tell me how many whole atoms we have here. We are going to do the same thing here. And here I want you to do more on your own. So all we need to do is to know how many whole atoms we have per unit cell, and then we need to find the relationship between A and R. This is all we have to do. So how many atoms per unit cell? How many? 4? 4? There are 4. So you see 3 plus 1, 4. This is how I put it. So we have like 6 on the faces, each one is half. So this gives us 3, and then 8 at the corners, 1 8 is 1. So 3 plus 1. Now, try to develop the relationship between A and R on your own this time. Looking at this figure, it's actually pretty simple. What we know is that they are touching here. That should give you the idea. Try to derive it on your own. Ask to see 3 correct answers. So talk to your neighbor, ask 3 questions, whatever you have to do. I know the answer is written in the next slide, but you need to show me how. It's simpler than what I see or thought. It's simpler. Correct answer for So I have 3 correct answers. Surprisingly, using different geometry. So if this is A, this is A, this is 4R. So basically, so this gives you the relationship between A and R. Just looking at this. But some of you have used different ways. It's fine. You can look at different ways. As long as you see the correct answer. So if you write A in terms of R, it will look like that. So try to fill up here how many whole atoms we have. The coordination number we didn't talk about, but you can convince yourself that You actually have 12, you have 8 plus 4. So 8 like previous one, 4 on the x plus 12. So, of course, I'm now asking you to calculate APF. You have the number here, try to write it down, see if you get the same answer. This is pretty straightforward. So we do exactly what we did before. Here is 4. So let me write something that there was a question. So how do we go? So you can write this as, I didn't write it before, so don't want you to be confused. So this is exactly the same as saying that A is 2 times the square root of 2r. One other question, which is a good question. Yeah, so for coordination number, if you want to visualize why it is 12, I think this should be helpful. To take any atom, let's say one on the face, then you can see there are 4 around 4, 4. In face center cube, there is nothing in the middle. That's why it's 12. Ask me, I try to explain to you more if you can't visualize it. I understand. Okay? So if you do the calculation here, we will get an even more densely packed structure, 0.73. So we have 4 atoms, and this relationship, however you can put A in terms of R. It doesn't matter. They cancel out, and you are going to get a number. Any questions so far? I give 30 seconds for everyone to write down. And the last one is hexagonal, where we are not going to spend too much time on. So, for example, zinc and titanium, they have a different microstructure. It's hexagonal close pack, HPC. And here also you can calculate the atomic packing factor, coordination number, and number of atoms per unit cell. This is not very, the materials which have this kind of a structure are not of so much interest to civil engineers, so we don't talk about this a lot. But you can check to see if you can get the same APF here. Now, I kind of casually asked you to think about the relationship between APF and density. It turns out that if we look at the macrostructure, we can calculate the theoretical density of materials. So the density is always mass over volume. So theoretical density is mass of the atom inside the unit cell over the volume of the unit cell. And the formula looks like that. So we have the number of atoms per unit cell that you are now all experts how to calculate for any kind of a structure. And then you have to multiply this by atomic weight. So you have to know how much each atom is actually weighted. That's important. And then we divide it by the volume of unit cell, and we have to correct it with a scaling number, Avogadro number, that it's just a constant. It's always the same thing. And this relates the number of atoms to mole, because atomic weight, you have seen it before, it is in kilogram per mole. Straightforward. Let's do a simple example. So here we have material with BCC, macrostructure. The atomic weight is given, the radius is given, and kind of this you need to figure out normally yourself, but this is also now given. So you just need to plug in the numbers to calculate the theoretical density, and be careful about the units. Nothing special, so try to just plug in the numbers. Look at the formula once again. Write it down for yourself from the previous slide. Can I actually pick up the previous slide? how many atoms per unit cell? What is the relationship between A and R? So the volume of unit cell is A cubed. The volume of unit cell is the volume of unit cell is A cubed. And you know the relationship between A and R because you know it's physical. There are questions like this in your homework, so it's important that you a nanometer is 10 to the minus 9. So we have millimeter, micrometer, nanometer. 10 to the minus 3, 6, 9. What is the unit? Don't forget the unit. Running out of time. So it is PCC, so we know we have 2 atoms per unit cell. This is gram per mole. It's very useful to write the units so you kind of see what's going on. This is atoms per mole. And here is A cube. And the relationship between A and R, because it is PCC. You already talked about this. And we should get something about 7.2 gram per centimeter cube. I saw that some people had put here the volume of the atom. No, it's, you want to see how much mass you have within your unit cell. So the volume is the unit cell, how much mass of the atom you have inside. So it's really mass divided by volume. Your nanometer is 10 to the negative 9. Okay, so the homework is due on Friday in case you are traveling or something. Please leave it in my mailbox before the time.